So good morning to all. I am very happy. So respected Principal Dr. M. Karthikeyan sir, respected our HOD M. Fischer K. Kandasamy, Department of Chemistry and Head, and Organizing Committee Ms. R. Anandarasu, T.V. Shangida Madam, and Kalaipriya, and Webinar Coordinator S. Pridhiba. So totally this is KSR Women's College, Tiruchendur. I am very happy to introduce myself. I am Dr. Mohanraj from Nannmaniyam Sundara University Constitutional College, Kanyakumari. So I would like to thank, special thanks, Dr. M. Kandasamy sir, gave me a wonderful opportunity to deliver my talk on the basic concepts of stereochemistry. So before my speech, I would like to special thanks BSc Chemistry students. So once again, good morning to all. Let's start my presentation. Okay. So it's very good. I'm very happy to privileged by the Department of Chemistry, the national level webinar on the basic concept of stereochemistry today. So I am inviting to this topic, the basic concept of stereochemistry. So what is stereochemistry? So before I'm going to my present, so I would like to tell about the historical perspective. So it is introductions. Just you think that why we study about the stereochemistry, a very important topic. Okay, the word is very important. Stereochemistry. Stereochemistry means stereo means what? Here the very fantastic word. The stereochemistry means deals with the chemical and biological. So very important topic. Chemical and biological constitution of the arrangement of atoms in space. Atoms in space. Just imagine the any molecule in space, right? So deals with the study of the molecule as a three-dimensional space. Three-dimensional space. That is called as we are stereochemistry background, right? So it is deals with chemical and biological both. So he is the history of perspective. Louis Pasteur, a wonderful scientist, we know very well. 1822 to 1895. He is 1847. He repeated earlier work of racemic acids. Racemic acids, the crystallization of sodium ammonium salt, given the mirror image crystals that he separated by hand. Equimolar solution of separated crystal have the equal but opposite optical activity. Here is what is the message. He crystallized one compound, the sodium ammonium salt. This molecule gives to mirror image crystals. Why the molecules act as a mirror image? It is something different in hand. So equimolar solutions separated in crystals equal about the opposites. Opposites means optical activity. These molecules give the optical activity. So here first mind it, the French chemist and microbiologist, the Louis Pasteur in 1884 to 9 is the first demonstrator of the microbes cause the specific disease of us by the historical perspectives. The French chemist Louis Pasteur was the first to reveal that the optical activity at the molecular level was due to the symmetry placement of atoms in molecule. Symmetry placement of atom in molecule. He further recognized the enantiomer has equal and opposite effect of polarized light. So this is the way of stereochemistry started, right? Year 1822 to 1895. His research. You see just a tetravalent nature of carbon, right? Why you see like this? Here you think that this is a very important molecule, carbon having 4 valence. So this tetravalent nature of carbon already we know very well. Okay, why the careful describe correctly the tetravalent nature of carbon. Why the chemistry was however still the view of two-dimensional way until 1874. Only the view of two-dimensional nature. Okay, want hub and label added in third dimensional of carbon. So that time they proposed that the 4 bond carbon are not randomly oriented in, but have to specific spatial orientations there. You see, this is for the 3-dimensional arrangement. Carbon is center atom and 4 carbon hydrogen is located in different space. One is the plane, another one is the back, behind and back position, right? Here the bond angle is 109.5 and here the 1.09. That is something different in tetravalent nature of carbon, right? Why? So this type of proposed structure of 4 bonds of carbon is not randomly oriented, have the specific spatial arrangement. So this is the first invention of tetravalent nature, the 3-dimensional nature. The Van Hoff get the Nobel Prize in 1901. Further advanced idea and proposed that the 4 atoms in which carbon atom bonded with corners and regular tetrahedral shape with this carbon in center. Okay, you think that its molecules rotate in space. You just imagine that molecule is rotated in space. It is easily rotated. Okay, it is easily rotated. You think the representative of tetrahedral carbon atom shows the convenience of use to show the 3-dimensionally arrangement. Three-dimensionally arrangement. Shows used to the solid lines represent the bonds. This is for line. Okay, plane of the paper and solid wedged line of representation to come out of the plane of the paper towards our eye, right? So this is the fundamental concept. Okay, now let us go to organic chemistry. I'm going to talk about what is organic chemistry. So what is stereochemistry? First you distinguish both, right? Organic chemistry is a study of carbon. It is compound and their properties. Already talking about nature of carbon. Here we are talking about the organic chemistry is study of carbon and its compound is their properties. Name of organic chemistry comes from the words organism, here in 1828. All organic compounds have been obtained from the organism and the remains. It's believed that was the synthesis of organic compounds from inorganic compound and the laboratory was impossible, right? It is the other branch of each substance derived from the non-living matter, minerals and is like it was called as inorganic chemistry. So you think that it's both different. What is inorganic? It is very important. Non-living matters and minerals like that is called as a inorganic. Organic is completely, it is living organism. It is a living. I believe that the synthesis organic compound. It is a compound having the living organism means plants and animals. Okay, so plants, animals compound is organic compound and it is non-living matters, minerals that is called as a inorganic compound, right? What is organic chemistry? It is a French nobleman, Lavoisier. It is provided the clause that shows the chemical composition could be determined, identifying and measuring the amount of water, carbon dioxide and materials produced the various substances were burned in air. Combustions of analysis soon established the compounds derived from the natural source of containing carbon. Early in 19th century, John Jacob Berzelius, who is 1807, coined the name of organic chemistry. So who is coined the name of organic chemistry? John Jacob Berzelius, from the study of the compound derived from natural source. So this is for organic chemistry, right? You see, this is the total periodic table. So element is predict that it is S block, P block, D block and F block. Here hydrogen, carbon, nitrogen, oxygen, sulfur. So this thing is role in organic chemistry. So here the other is metals or non-metals, some radioactive elements. But organic chemistry, so most predominant element is only for hydrogen, nitrogen, oxygen and sulfur, right? So this is the fundamental nature of our compound, right? Okay. So Katasami, it is visible? Okay. I think it is something, right? One second. Okay, let's start. It is a introductory point here, talking about just wait. One second, I presenting again. Wait. Okay, so stereochemistry, it is a very important concern. It is visible. Okay. Some network problem, right? Okay. Broke throughout even of organic chemistry in 1828 when the German chemist the Friedrich Holler in 1882 heated a sample of ammonium cyanide NH4OCN and converted it into urea NH2CO NH2. It is an organic substance earlier isolated from the urine. So this is the first chemical reaction. It is isolated from ammonium cyanide inorganic compound. It is a byproduct is urea. The ammonia is an inorganic material where the urea is waste product of urine mammals in the organic ones, right? Here, the result of Fowler, the research, the definition of organic chemistry changed. The view of definition was based on the observation that every compound discovered in living organism had one properties of common. They all contain the element of carbon. The resulting of modern definition of organic chemistry, that is study of organic compound, was adopted, right? Okay, here the scientist Jacob Berliusens and Friedrich Holler and Antonin Lavoisier, right? Importance of organic chemistry. Extensively natured material for the treatment of illness. Here 2500 to 3000 BC, right? Birth of Christian. So only extensively used to natural material for treating illness. Yes, in case of everybody have some illness, so suddenly they are treating with organic compound, right? Okay, in 2500 BC in India, indigo was a dye cloth. Indigo, is a plant of indigo plant. It is used as a dye cloth. A deep blue, almost all drugs prescribed today for the treatment of the disease are organic compound. Some are derived from the natural source, many other are the product of synthetic organic chemistry. Okay, so the before 2500 BC, the Indian peoples are used to only for indigo is an organic compound is using of the dye. So nowadays they are using the many organic compound. It is organic compound only. Okay, right. So nowadays the over the 19 billion organic compounds are characterized, including food we eat, made of carbohydrate, lipids, proteins, and vitamins. First, and it is a plastics, rubber, and cloth and proper made of organically based on compound, synthetic dyes, drugs, insecticides, herbicides, and perfume and flavonoids and the agents of some petroleum product. So this is for the 19 million of organic compound is characterized, right? Challenging and opportunities. What is challenging and opportunities? Petroleum and natural gas provide the building blocks of the construction of large molecule of many drugs, plastics, synthetic fibers, films, and elastomers are made of the organic chemical obtained from the petroleum, right? Here, very important most process of chemical industry carried out of the presence of catalysis and new catalysis. We learn to great deals of biochemistry. The chemical reactions takes place that the living organism of catalyzed by enzyme. So genes splitting technology and method of determination of species molecular structure of DNA are just two of the tools driving to the next scientific revolution. You are studying the organic chemistry at the time of its great influence on our daily lives, right? And computer and organic chemistries nowadays we are totally organic chemistry to found the graphics capability of the mini computers, workstation and personal computers, and we will suited to visualize of molecules of three-dimensional object, assisting the ability to interact with another molecule, right? Here one is a history of Big Bang. So how the molecule is created? George German in 1948 suggested that the universe was to create with the hot Big Bang. You know, the various elements such as hydrogen and helium. Hydrogen and helium. You most think that it is a Big Bang theory is how to form this world, right? How to form this galaxy, how to form this surrounding. The first such as hydrogen and helium would produce to the few minutes of immediately after the Big Bang due to the extremely high temperature and density of the universe of this time. High density would cause to rapid expansion, right? The university expanded to hydrogen and helium would cool the contents into stars and galaxies. So the basic material is hydrogen gas and helium. It is the combustants, right? Today, due to the continuous cooling, the radiation left over from the epoch of the recombination, when the natural and it's a neutral atom are formed, right? Production of hydrogen and helium during this time instead of just hydrogen burning in star would explain why the hydrogen helium ratio of the universe is higher than would be what could be produced by the star alone. So it is a basic thing. It's a galaxy or stars, everything is formed with the hydrogen and helium gases, right? Here, where did the carbon compound form, right? According to Big Bang theory, universe becomes expand to about the 12 million years ago, when it is incredibly dense in 1096 GCMS 3, incredibly hot 1032 K ball containing of all matters in the universal of exposure. Here, two neutrons and two protons, the combustants in the helium nucleus is formed. Then, three helium nucleus to form two nucleus of carbon 12 it is formation. This is for the universal expanded cool to positively charged protons and helium nucleus combined with the electron to give the hydrogen and helium atoms together to hydrogen and helium 99% to mass of the universe, 99.9% of atoms. Hydrogen is the most abundant elements, 88.6% of atoms in universe are hydrogen and 11.3% are helium. So basic material is hydrogen and helium. Hydrogen, you know very well, hydrogen is one atom and one proton and one neutron and it's one electron. It is helium is 2 and 2 proton, 2 electron, right? This is for three types of three helium nucleus combustion and formation of carbon is formed, right? So fusion of the nucleus carbon 12 with one of the helium gives to oxygen 12. So this is the fundamental idea of carbon comes from world, Big Bang theory, right? Why I give this type of lectures, right? First, every students must know that why the basic concept of stereochemistry. Every chemistry students know the importance of first the tetravalent of carbon and what is organic chemistry and what is organic chemistry, who is given this history and periodic table, and it is invention from the artificial organic compound from inorganic compound to organic compound, right? And then it is many of the opportunities there. Important organic chemistry, there are the many. It is ancient Indians are using indigo cloths and dyes. Nowadays they are using the many synthetic organic chemistries, drugs, right? So this is for the fundamental concept of many applications of plastics, rubber, cloths, and based on this structure, right? So this is opportunity at the Big Bang theory in carbon. Here talking about the stereochemistry. Every molecule organic compound having three-dimensional shapes, it is used to stereochemistry, stereochemical activity. First of all, you know that already I told that what is stereochemistry. The stereochemistry is the branch of chemistry that deals with study of the three-dimensional arrangement of atoms in space. Already I told you, the stereos means solids, right? The stereochemistry branch of chemistry that deals with study of three-dimensional arrangement of atoms in space, right? That is called as a stereochemistry. Stereochemistry is two types. The major divided in two types. One is structural isomerism, another one is stereoisomerism. Actually, it is a three-dimensional arrangement of molecules in stereoisomerism. Basically, isomerism is divided in two types. One is structural isomerism, another one is stereoisomerism. What is structural isomerism? So, molecular formula the same types of bonds, but the different bonding of sequences, connectivity is important. That is called as a structural isomerism. But stereoisomerism is totally different. It is about different spatial arrangement and relative orientation. Have to the same molecular formula, but same bonding is sequencing is different, right? That is called as a stereoisomerism. Here, on flow chart for isomerism, what is isomerism? You know very well. It is the same molecular formula, different structural arrangement, different physical and chemical properties is different. But the stereoisomerism is two types. One is the constitutional isomerism and stereoisomerism. So constitutional isomerism 5 times. One is the chain isomerism, position isomerism, functional isomerism, metamerism, tautomerism. But the stereoisomerism is two types. One is configurational isomerism, another one is conformational isomerism. Right? Here talking about it is a stereochemical cis-trans isomerism. Here talking about cis-trans isomerism. Stereoisomerism, the cis-trans isomerism contain the chiral center. We generally simply stereochemistry dividing conformation and configurational, but the stereoisomerism, configurational isomerism, there are two types. One is cis-trans isomerism, isomeristic that contain in the chiral center. This is for geometrical isomerism. This is for optical isomerism. Geometrical isomerism, optical isomerism, right? Here the stereochemical form is cis-trans isomerism. What is means cis-trans isomerism? In case geometrical isomerism means carbon-carbon double bond having carbon-carbon double bond and 4 groups is located. In case of carbon-carbon double bond is formed, that is double bond is cannot be free rotated because of some restriction is there. Bi bond and sigma bond, it is not rotated. So here the restricted rotation is there. So two molecules belongs to have the same connectivity but not identical. Same connectivity but not identical. In case of along with carbon-carbon double bond, this is methyl group, this is methyl group is same. This is hydrogen same. This molecule is cis isomerism. Otherwise, it is oppositely located in carbon along with carbon-carbon double bond. This is called as a trans isomerism. So already talking about the carbon having 4 groups, carbon and central group, that is 4 group tetravalence, and here the 2 carbon is located from carbon-carbon double bond, right? Another here naming of alkene stereom, EZ notation system. Cis-trans isomerism overcome to EZ notation. It is advantages of cis-trans isomerism for EZ, right? Here first of all, the geometrical isomerism. What is geometrical isomerism? Here, the example of one of the important point, it is geometrical isomerism. What is geometrical isomerism? It is the restricted rotation around the carbon-carbon double bond. It is not the response for the geometrical isomerism. Here, you see the carbon atom and double bond. Another one is same color is this is the same atom. Here the same atom. You give the cis groups, right? Cis atom. Either the same molecule is the trans group is oppositely located in carbon along with the carbon-carbon groups or atoms are opposite sides cross the double bond. So this is for geometrical isomerism in alkenes. Geometrical isomerism in alkane, right? So isomerism therefore have the different physical properties, example boiling point and density, and have the similar chemical properties in the most cases, right? The restricted rotation for carbon-carbon double bond. Here the single bond in case of can easily rotate. You see this one animation is formed. All restricted are the same because of the carbon single bonds have the free rotation. The single covalent bond can easily rotate. So this is for conformation. This is for conformation. In case of carbon-carbon double bond, it is a restricted rotation. This is for geometrical isomerism. This is for geometrical isomerism. So cannot rotate the carbon-carbon double bond, but the carbon-carbon single bond is free rotation. This is conformation isomerism, right? Another one point, you see carbon-carbon double bond is restricted rotation. The groups and either end of the bond are from Rosen in one position. Isn't easy to flip between the two. Here you see one carbon is blinking here, right? Another the same atom is blinking here, right? The produce the two possibilities, and the two structures cannot be interchange easily, but the atom is two molecules occupy the different position in the space, So this is for important for the restricted rotation of carbon-carbon bond. Here you see, right? Another, this is the triglycerides and unsaturated fatty acids. Naturally, we are using the cooking oil, the saturated or unsaturated, the cis trans fatty acids is there. You see here the cis and trans atoms, right? Another, the stereochemical notation. Here, in case of carbon-carbon double bond having 4 different groups, it is formed. That is complicated to find out the cis trans isomerism. So certainly we are going to discuss about one advantage, that is called as a EZ rotation. Cis trans are useful when substituted with identical or unlike, but oleic acid, unsaturated fatty acid has the cis double bond. Here H's are the identical, and cis trans reference to ambiguously when the analogy is not obvious, right? Here, for example, for chlorine, bromine, chlorine, hydrogen, the 4 different group is formed. When it is a 4 different substitution is there, cis trans does not work. So you need one advantage, that is EZ configuration, right? Systematic body of rules for ranking substituent must be used, which is the related to but different from the cis trans isomerism, right? Here EZ notational system is very important. This is for advantages of the EZ notation. What is mean by E? The higher ranked substituents are opposite sides. That is called as E. E means antagon. Z is higher ranked substituents for the same side, are together. This is for the same. That is means Zusammen. E Z. E Z notation. Considerably, here each sp2 carbon atoms and double bonded separately. In carbon-carbon double bond, it is used and the higher priorities, ranking pair of substituents related to each other. How to give the name? So in case of cis trans isomerism is freely and easily due to in case of molecules same side, it will give the cis isomerism. In case of molecules in opposite side, suddenly you give the trans isomerism. But here you see the 4 different group is there, but it does not give the cis trans isomerism. Here it is one rule for EZ notation. What is another rule? Here another one important, priority orders. Priority orders here very important. Which one atom is a higher atomic number? That is the preferentially first number. Preferentially first number along with the carbon-carbon double bond. Higher ranked substituents. Higher ranked means higher atomic number, right? Higher atomic number. That is called as E is here higher number, lower number. Lower number, higher number. Opposite. Along with the carbon-carbon, opposite. Higher and lower. First you give the carbon-carbon, higher, lower, and along with the carbon-carbon double bond, you calculate here the opposite. That is called as antagon. In case of higher is there, the same side, lower is there. That is called as Zusammen. So molecule having antagon, it is opposite. Zusammen is same side. Based on priority order. Priority order means the atomic number. Here using ranking. How to give the ranking? So here the very important point, that is higher, lower and lower, higher antagon, and higher and lower. This is Zusammen. This is another one. 3 important scientists. Kahn-Ingold Prolog CIP system. CIP rule. They give some rules and regulations. So this is a system is used for the deviated by the RS Kahn Sir Christopher Jinkold and Vladimir Perlak. The three scientists, they give the one rule for the ranking group of devised from the another kind of stereochemistry. Chirality, but have to adapt it to alkane stereochemistry, right? Alkane stereochemistry for higher atomic number outranking low atomic number. So first rule number 1, CIP rule, they give the rule number 1. Which one is the higher atomic number? That is first predominant one. Another next atom. It is a higher atomic number outrank lowest atomic number. So in case of here bromine, chlorine, hydrogen, fluorine. So you see this carbon, bromine and fluorine. Which one is the higher atomic? Higher is bromine, atomic number bromine and Pp, and fluorine is compared to low of bromine, right? Another here chlorine and hydrogen. So don't think it is a chlorine is a higher atomic number and hydrogen is lower atomic number. You give the lower number. You give the bromine is number 1, fluorine is number 2. Here chlorine is number 1, hydrogen is number 2. You now you see which molecule is higher, lower. This is for Zuzamine. Z 1 bromo, 2 chloro, 1 fluoro, ethane. 2 Z 1 bromo, 2 chloro, 1 fluoro, ethane. This is the first rule number 1. Higher atomic number, you give the preference number 1. In case isotope is formed, which one is the isotope? Is hydrogen and the deuterium is fine. In case of deuterium is first and hydrogen is next. The third rule is it is two atoms are identical compared to atoms attached to the on the basis of their atomic number. Proceedings the established by the atomic first point of difference. Here is the same molecule attached here. You see carbon and carbon. Your ranking of the first carbon atom is give. At the same another one is carbon is given. You look at next atom. This is for rule number 3, right? Another rule number higher. Which one is the higher and lower? First rank rule number the period highest atomic number is given to first. Second is isotope is come. It is higher isotope number is given the first. And third rule is in case of the same atom is located in carbon-carbon double bond, you look at the next atom, that is rule number 3. Another point, the higher rule for in case carbon-carbon double bond, carbon-carbon triple bond is formed, it is equivalence. The atoms, the double bond or triple bonds to be another, it is considered to be the replicated to as the substitute on the atoms. So in case of you see carbon CH double bond O outranking for the CH2 OH. And COOH, here COOH higher, it is here COHH lower. So this is for CIP rule. The 4 rule is important. First rule, it is a higher atomic number, it is a first preference to give the carbon-carbon double bond. And then second is isotopes in form, that is called as higher isotope is you give the first number. And third is in case of same atom is located in same connectivity. You just look at the next atom, and third is double bond triple bond is formed. You look at the consider the replicated as the substitution on the atom, right? CIP rule. Okay. Here you think that it is a free rotation about the single bond. So if you the carbon-carbon has a single bond is there, it is a free rotation is possible. Here double bond is already I told that it is a restricted rotation. Why? I'm here talking about the two different atoms groups attached. Here you see the different atoms or groups attached, basically the geometrical isomerism. But here you see 1, 2 and 2, 2. Similar group atoms are attached. It is basically it is the two similar atoms or groups attached. This once you get the similar atoms or groups attached to end of the carbon-carbon double bond cannot be have the geometrical isomerism. Definitely geometrical isomerism not due, right? Here the two different atoms or groups attached here. This is for geometrical isomerism. Based on the EZ rotation is possible. Here it is cis-trans is possible, but in these 2R is not for to get the similar atom groups attached to carbon-carbon double bond cannot give the geometrical isomerism. You think that in case of two atom is same, it is another two atom is same. So this complicated. Another is 3 atom is same, 1 atom is different. So you cannot give the geometrical isomerism, right? Another, this is for one example, chlorine and chlorine opposite side. This is for the trans isomerism, and then chlorine is same side, that is called as cis isomerism. Here they are talking about methyl is opposite. This is a trans butene, butene, and then cis butene. Example. Geometrical isomerism is summarized. To geometrical isomerism, if you must have the restricted rotation, often to involve the carbon-carbon single bond and double bond. Introductory purpose. The two different groups are the left hand and end of the bond is two different groups of the right hand end, right? That does not matter to whether the left hand group and to same of the right hand are ones or not, right? So another important point here, the geometrical isomerism is over. Another point, the configurational isomerism, another it is optical isomerism. So geometrical isomerism, we are talking about carbon-carbon double bond restricted rotation. That is geometrical isomerism. We discussed here the cis trans and EZ, right? Here the optical isomerism. What is optical isomerism? It is any compound, any organic compound, inorganic compound passed through plane polarized light. It is the molecule having the ability to rotate the clockwise rotation and anti-clockwise rotation. That is called as a optical isomerism. You see, this is a sodium lamp is ordinary. This ordinary lamp is converted to monochromatous. The polarized light, polarized filter. Here the sample is inserted here. It is passed through the plane polarized light. It is molecule act as an analyzer. Clockwise rotation and anti-clockwise rotation. Clockwise rotation, anti-clockwise rotation. It is very important. The molecule as clockwise, dextrorotatory, plus rotatory, and the molecule is anti-clockwise, that is called as levorotatory. Here you see dextrorotatory is plus rotation, levorotatory is minus rotation. Commonly the drug is noted with D or plus or L or minus, not related to the R and S configuration, right? Here specific rotation. How to identify the specific rotation? Observed rotation depending on the length of cell and the concentration as well as the strength of the spatial activity, temperature, wavelength of light. Here alpha is equal to alpha observed and C dot L. Here alpha is observed in the rotation of observed in the polarimeter. C is the concentration of gram per milliliter. L is length of sample cell in decimeter, right? Here one word very important, chirality. What is meant by chirality? Right hand, in case of you show it a mirror, so oppositely our right hand is showing mirror in left hand. So this is totally, in case of our hand, right hand, it is oppositely showing left hand, that is called as a chirality, because of it is oppositely, totally hand gloves does not fit for left hand, right? It is object of chiral if it is mirror image is different from original object. Achiral, the mirror images that can be superposed to achiral. So this is for the chair, it is shown in mirror, it is not any differentiation. So but hand is right hand to left hand is so. This is called as a chiral. Another way, this is for the chair. This is the same image will be showing mirror. So here the chiral and achiral molecules. What is meant by chiral and achiral molecules? Although the everything has a mirror image may or may not be the superimposable. Some molecule like hands, left hand and right, left and right hands are mirror images, but they are not identical. Means non-superimposable. Our mirror has a non-superimposable object and molecule that is superimposable and their mirror image or chiral, right? Okay, the molecules in case of left hand, you give the mirror image is right hand, are non-superimposable. Is not matched. Okay, and these here is some example clothes and hands and socks. Okay, left to right and right to left to right. Here the molecule is act as a same type. Here the go back of dashed, dotted line wedged. You see the center is carbon, this is a plate, this is the plane of paper, and goes to back, dot dot line. In case of any compound you see, put it the dot dot line. In case of molecule is in back side, right? Another comes to forward. This is the forward molecule or behind the molecule, right? Now remember that the bolt, the wedged, the representation bonds comes towards you out of the papers, and the dashed bonds represent the bond going away from you into the paper. Okay, here you see the same molecule is project way off from the viewers. Here the carbon and dotted line you see that goes to back. This is come to forward. This is the plane of paper. The convention of use this back book is the projections of forward to view here like this, right? This is any molecules you see like this. It's the, in case of line is there, that is called as the plane of the paper. In case of dot line is there, this goes to back. This comes to forward. This is a molecule. It is behind the molecule, right? Stereoisomerism. Here talking about the enantiomers. Here one molecule is what is enantiomers. Here the two word is important. Enantiomers and diastereomers. Enantiomers and diastereomers. Kandaswamy, it is visible or audible? Slide is visible. Okay. Thank you. Okay, I will continue now. Right. Here, one word is coined, the enantiomers. What is meant by enantiomer? Okay. Okay, shall I continue? Sir, shall I continue? Okay. Here, another word is a stereoisomerism, enantiomers. What is enantiomer? Enantiomer word is very important. Enantiomer and diastereomers. Here talking about the compounds that are non-superimposable mirror image. Any molecules that is chiral must have two enantiomer. Here the carbon, you see the carbon. This is another different molecule. This is one different molecule. This is different molecule. This is different molecule. If you give the mirror image, suddenly the molecule is give to opposite. This type of molecule is enantiomer. Simply we called as the carbon having four different groups. That is called as chiral molecules or enantiomer molecules or asymmetry molecules. These type of molecules give to mirror image, right? Otherwise, it is a symmetry molecules that is not give to mirror image. Okay, here the chiral carbon atom. You see, this is a central carbon atom. The four different numbers. Here 1, 2, 3, 4. You think that it is a four different groups or atoms. The mirror image is definitely a 3 to 4. It is definitely opposite. The carbon and carbon atom that is bonded to four different groups is chiral. The mirror image will be the different of compound. This is the molecule. This molecule having the enantiomer. In case of simply you mind it, the carbon having four different groups, that is called as enantiomeric molecule. Four different groups, that is called as enantiomeric molecule. The enantiomeric compound having the mirror image. The enantiomeric compound having optical isomerism. The enantiomeric compound give the clockwise rotation and anti-clockwise rotation. Okay, simply this molecule is called as a chiral carbon molecule or chiral carbon atom, right? So serious center, that is a asymmetric carbon. In case of four different groups, that molecule has the asymmetric center, asymmetric carbon center or chiral center or stereomeric center. If you give any word, it is every word is correct. Asymmetric carbon, you give the total word. This is asymmetric center, chiral carbon center. It is totally the molecule having the enantiomeric molecule, right? We give the both name for chiral center, stereo center, and it is a double bonded to carbon atom. Cis-trans isomer is the most common type of the stereogenic center. For example, you see here the dashed wedged line. The carbon is here the four different groups: hydrogen, bromine, methyl, and CH2CH3. You see these are asymmetric center or chiral center or asymmetric carbon or chiral carbon. Whatever you give the name is in every molecule is correct. Here the asymmetric carbon. You see here the nitrogen is different. It is the same under the 4 different group. This is also called as a chiral center. But stereoisomerism, stereo center, here you see that carbon-carbon double bond. Here carbon, hydrogen, methyl, and here another one carbon is 2 is there. It is called as a stereo center, circled, right? The asymmetric carbon atoms are example to chiral center, which are the example for it is a stereo center. Which are the example for the stereo center. Here you are talking about the R enantiomer, S enantiomer. It is a match. It is a binding with another receptor. Here ball is same. It is matched round. This molecule is matched here. This molecule is matched here. Okay, just you bind it site of receptor. But here the binding of receptor here is ball. It is not matched. Here is another one is pair. Here is a round circle is not matched. Here is this is for S enantiomer. This is for R enantiomer. So this is for superimposable. This is superimposable molecule. This is non-superimposable molecule. Right? Here the achiral molecule. Achiral molecule is superimposable molecule. Here carbon 3 3 1 1. The 3 3 is same molecule. If give the mirror image, this is not give the mirror image. In case of the 128 degree is rotate here, right? If the same molecule is same here, same this type of molecule is achiral molecule. So chiral molecule is carbon 4 different groups, but here the achiral molecule is carbon. See, any 2 molecule is same. Any 2 molecule is same. That molecule is not give the mirror image. If the it is a different, you rotate the 180 degree, like the same structure of the formula. Take this mirror, this image, is try to superimpose it on it. The one to left, the matching of all atoms, everything will match, right? Here, when the image can be superimposed, already I told you, here it is superimposed. In case of molecule is matched, that is called as a superimposed molecule. Superimposed molecule, right? Here, another one talking about in case of molecule having the when image is superimposed, that is compound is the achiral molecule. So here we are discuss about chiral molecule and achiral molecule. In case of chiral molecule, carbon having 4 different groups. That molecule gives the mirror image. So you easily find out the clockwise rotation and anti-clockwise rotation. That molecule having the mirror image. In case of achiral molecule, in case of any 2 molecules similar, that molecule is not give the mirror image. It is a superimposable mirror image. So these molecules act as not give the mirror image, right? Okay, this is called as a AMA. Plane of symmetry. What is mean by plane of symmetry? You just view this angle, carbon 3 3, the same molecule 1 2. The plane of symmetry. You put it the Fischer projection. Fischer projection. Just that 1 2 3 3 same. You give the sigma plane of symmetry. The molecule that is plane of symmetry is achiral, right? Here talking about already first introduction slide is give the it is Louis Pasteur the racemic mixture. In case of any compound is plus and minus is there. 50% of plus rotation and 50% minus rotation, right? Here the plus 13.5 degree rotation minus 13.5 degree rotation. The racemic mixture contains the equal amount of the 2 enantiomeric mixture. So this is called as a enantiomeric. Equal amount of D and L enantiomers, that is called as a racemic mixture, right? And notation DL or plus or minus or no optical activity, right? So the mixture may have 2 different boiling point and melting point from the enantiomer, right? This is for a racemic mixture. Okay. Another one important point is resolution. In case of compound having the plus or minus is totally separated from plus to minus, and this molecule is resolution molecules, right? So Louis Pasteur is putting this type of research, right? Another one is important point, absolute configuration. Basically, we are generally called as a RS system nomenclature. The ranking of 4 groups atoms is bounded in the chiral center. Already I told you CIP rule, con equal to log rule. The same rule here you implemented here. In case of how to predict the RS. What is meant by R? It is a rectus, it is a sinister. Rectus, it is clockwise and anti-clockwise rotation of nomenclature. It is for the advantages of DL rotation, DL notation. These are 4 rank group, for atoms bonded in chiral center. In case of carbon having 4 different groups, in this highest priority 1 and 2, 3, the least is 4 is lowest priority, the highest priority. There is no direct correct correlation between the R and S configuration and its relatively configuration of optical rotation, right? Here the same we are talking about the Conformational Isomer CIP rule. It is the same, the rank substitution of the stereogenic carbon according to the atomic number. Which one is the highest atomic number? You give the preference number 1. Another, in case of orientation, lowest rank substitution point, it is way from you. You just think that is car driving, car steering. Okay, 3 steering is having the 3 bonds, and it is located in the last rod, that is called as here. It is like that. You see, you think that like a car, you like that this is for steering. This molecule having 3 bond. Okay. Another one is rod. This is for lowest. You operate, right? This is a rod. This is the lowest molecule. This is hydrogen is lowest. Another one is 1, 2, and 3. You think that like steering. Think that like steering. Okay. The molecule like steering. This is a important point of RS configuration, right? Conformational Isomer. So treat of single carbon atoms like the ranking of molecule. Another one, it is a orient of molecules that is lowest ranking substitute molecules from away, right? In order to the decreasing procedure, trace the clockwise path and absolute configuration is R. If the path is anti-clockwise rotation, it is called as a configuration is S. You simply mind that clockwise is R, anti-clockwise is S. The first number we are given R is clockwise and S is anti-clockwise. Orient is lowest priority 4 away from you, highest 1. What more? Okay, you see the clockwise molecule, clockwise R configuration. How to find out this molecule? Actually, first you see the carbon having 4 different groups, 1, 2, 3, 4, and switch any 2 substituents and the new configuration is opposite. R is S, S to R, right? In case of molecule, clockwise R configuration, anti-clockwise, center clockwise S configuration. So designated the configuration, the group attached to chiral center are the same CS2 below. Okay, the analysis of atomic number and the next atom in the bonded to sequence adjacent atom. Here we see this is the central carbon atom, this is the central carbon atom, right? Here the 4 different group is there. So least group is 4 and highest group is oxygen. Because of oxygen having the 8 atomic number 1 and least atomic number hydrogen. So this is 4. Here another one is total group with the chi CH and then CHCS. The same group is attached. You look at the next atom, right? Here the predominant is to adjacent atoms, right? The CIP rule 4 rule is indicated this type of way. Next atom is for the same carbon hydrogen atom, right? Designate the configuration to double bond, count by the 2 single bonds. So if the CIP rule 4th rule implemented here, in case of double bond is there, it list of these carbon atoms having the, in case of adjacent to the carbon atoms counted the twice. In case of one carbon OH is passed, you give the carbon double bond, you put it the 2 atoms, 2 adjacent atoms count to twice. The question of the following molecules R or S. You see that here which one is R, which one is S. A molecule and R, B molecule and S. You see here the central carbon, chlorine and 2 groups. One is this is for A, this is for B, right? So this is important point of RS configuration, right? Naming from the perspective formula, ranking group of bonded asymmetric carbon atom. Here one carbon, chiral carbon, the 4 different group, 1, 2, 3, 4, right? And it is if the 2 atoms, if the groups are atoms which is the lowest priority is bonded into H wedge, right? Here the bromine and CH3, CH2 and CH3, H. Here the bromine number 1 and hydrogen is 4 bromine number 1. Here the carbon and the same bond is carbonate. You look at the next atom. So number 1, number 2, number 3, number 4. Right? The necessary rotating molecules, that lowest periodic group atoms wanted. Right? So if you like find out this based on the CIP rule, you can find out the cis-trans isomerism. Right? Cis-trans isomerism. Enantiomeric isomerism. So this is simply called as a dashed wedged line. Dashed wedged line. The dashed wedged line can easily find out S2 butanol and R2 butanol. So this is totally complicated to find out the RS configuration. Suddenly one scientist give some ideas for Fischer structures, Fischer projection. Horizontal bonds points towards U. This is for a simple method to find out the RS configuration, right? M.L. Fischer's 1815 to 1919 give the very wonderful research. He got the Nobel Prize in 1902. So he gave the rules for Fischer projection. There are 4 arrangement of molecules, that is horizontal bonds at the chiral carbon point towards U and vertical bonds point of the away from U, right? So this is towards U and away from the U, right? This is a 4 bond different groups. First, horizontally bond of chiral compound point towards U, horizontal. Horizontal means this is vertical. Vertical point of away from U, right? So this point is used for the Fischer projection, the molecule on page of cross. When the represented this way, it is understood that horizontally and bonds to onwards to vertically bond back of this molecule. 4 different groups. You write like this, okay? This is a projection molecules page in this class, horizontally, vertically, right? This is the question. What is the stereochemical designation of the indicator chirality center? This is the cross Fischer projection section. So this is here carbon. It is a diastereomeric molecule. It is a glucose. Here one chiral center. It is on 4 different group. Another chiral center 4 different group. Another chiral center 4 different groups. Right? AR and SR. So R and S configuration step to assign the priority, the relative priority to each of the bonding asymmetric carbon group 1 and have to higher priority number 1. Don't confuse. This is for the RS configuration. This topic is very critically to definitely go to read. So any chiral molecule having 4 different groups, enantiomer molecule, you write like that. It is a Fischer projection. Okay. Then you give it the find out the RS configuration. Okay. The Fischer projection, in case of if you get this type of dashed wedge line molecules, so suddenly you can write like this. It is a cross type of like this is called as a Fischer projection. Plot representation of 3D molecule. If the right molecule is a chiral carbon is the intersecting of the horizontal and vertical lines. Right? The horizontal line is forward of the out of the plane and vertical line is behind of the plane. Right? So this is a projection Fischer projection formula. You can write like this. Another one example in the 4 different group and you write like this horizontally and vertically. You can write like this, right? This is for the Fischer projection rule. Rule number 1, the carbon chiral, it is a vertical line and highest oxidized carbon atom top to bottom, right? Okay, simply you mind it rotate in 180 degree. The plane does not change the molecule and its rotation is 90 degree is not allowed. Okay, if any molecule is rotate 180 degree, any change is not does not change in molecule. So you can the first rotation is 180 is very easy to find out the RS configuration, right? 90 degrees is not possible. Here is the Fischer rule RS configuration. Here rule number is more than one chiral center is the carbon 4 different group. If you take this group 1, right? Another one is carbon 1, 2, 3, 4. 4 carbon is located. The second carbon having the chiral carbon, it is 4 different group. Another third carbon is 4 different group. Okay. So this is the lowest period. Usually hydrogen is come to down forward. So the assignment of are back. Clockwise 1, 2, 3 is S is the continue counter like 2. 1, 2, 3 is R. So already I told you is cost sharing. You like think that it is a 1, 2, 3 here. It is a 4 is lowest is least molecule, right? This is you can easily find out the molecules for RS configuration, right? Another point. You see, this is a clockwise 1, 2, 3 is S and counterclock it is 1, 2, 3 is R. Example for you see, already I told you this is first carbon, second carbon, third carbon, fourth carbon. Okay, here 1, 2, 3, you just think that it is totally taking up the group. First carbon is chlorine is number 1, hydrogen is number 2, sorry, chlorine is number 1, methyl is number 2, or another group is here. This is number 1, this is number 2, this is number 3, this is number 4 is least group, right? You get the configuration is yes. Another one is here, you take this group, the chlorine number 1, and this group is number 2, another methyl is 3, and the hydrogen is least group is S. Configuration is formed. 180 rotation is how to rotate the 180 degrees. If the write this molecule is Fischer projection, you suddenly take the 180. Here we are talking about hydrogen OH and COH CS3. You see this molecule is like the dashed wedge line. 180 degrees is rotated. You rotate 180 degree. What will be happen? The methyl will come to the top and COH come down. So write like this. This is called as a 180 rotation. So rotation of 180 is allowed because it is not will to 180 is allowed because the will not the change the configuration. 90 degree, if the rotate the 90 degree, definitely it is not possible. It is not enantiomer, right? Incorrect orientation, right? 90 degree rotation will change the orientation of horizontal and vertical groups, right? Do not rotate the Fischer projection of a particle. This is a fundamental concept of Fischer projection rule is very important and must every chemistry students very clearly the point, because if you find the RS configuration, definitely in case of molecule gives to dashed wedge line, you suddenly go to write the Fischer projection, then how to give the 180 degree rotation and not give to 90 degree rotation, right? So this is very important. This is another example for the glyceraldehyde. Here the glyceraldehyde Fischer projection you write like this. It is 180 degrees rotation. Normally hydrogen is front and it is due to clockwise rotation, right? Right. So this is for the hint to remaining the R and S from the Fischer projection. It's a hydrogen and horizontal bond towards to U instead of away from the U. Just apply the normal rule of backward, right? The Fischer project, the Fischer mirror image, easy to draw, the method is easier. The point enantiomers and interact internal mirror planes with the molecule have 2 or more chiral center. 2 or more chiral center. This is called as a racemic mixture. Already I told you 50% of R and 50% of S is called as racemic mixture or 50% of mixture of enantiomer. Right? The meso compound is internal plane of symmetry, optically active compound. This molecule is, in case of this is same plane molecule. This is superimposable. Right? This molecule is rotated 180. There is no any optical active. Right? This diastereomeric cis-trans isomerism, the double bond. Right? Here some example, and diastereomeric is more than one chiral center, that is called as a diastereomer. More than one chiral center, that is called as a diastereomer. Here the 2 enantiomer is there, right? 2 means 1, 2, 3, 4, right? 4 carbon is counted. It is second carbon having S rotation, third carbon having the R rotation, and then it is an optical mirror image. It is the same. It is 2 carbon having the R rotation. It is totally opposite, and third carbon is S rotation, totally opposite. This is called as a diastereomer. The same like molecule, right? Another, the molecules are 2 or more chiral carbon. You get the stereoisomerism, not mirror image, right? Okay, not mirror image. Here, already I told you, in case of get this molecule, it is totally opposite. Basically, the stereoisomerisms are not mirror image, the diastereomer molecule. 2 or more chiral center, when the compound having 2 or more chiral centers, they have the enantiomers, or diastereomers, or mesomer isomers. Enantiomer has the opposite configuration at each of corresponding chiral, and the diastereomer have the same matches in some opposite configuration. So meso compound having the internal mirror planes, right? So which one is the compound is 2, 2, 3, 4 tetrahedral? How to many stereoisomers in that? Just to find out the carbon having chiral center 4 different group 1, 2, 3. Here is opposite, right? Here one group is there 1, 2, 3. But here 3 asymmetric center is there. In case of any molecule, these options. In case of this is methyl, this is chlorine. Here one hydrogen is there. There one hydrogen is there, right? So 2 N is asymmetric centers of 8 stereoisomers, right? So this This is for the N3, 2N, which is 8, or stereoisomerism. This is the carbohydrate. It is our first carbon, and second carbon, chiral carbon, is R rotation. Third is S rotation. Fourth is R rotation. Fifth is R rotation. D glucose. Right here, the four chiral center is there. This is for the mesocarbon. The molecule having the same bromine, bromine, and hydrogen, hydrogen. 1, 2, 3, 4 molecules. This center is give this plane of symmetry. This is called as a mesocompound. This is called as a mesocompound have the plane of symmetry. If no one image was rotated 180 degree, it then could be the superimposed to and the other image. Right? Mesocompound are chiral, and even though they have the chiral center molecule. Right? Number of the stereoisomerism you can find out easily. Right? Properties of diastereomers. Diastereomers have the different physical properties, so that they can be easily separated. Enantiomer different only. The reaction which other chiral molecule and direction which is the polarized light of rotation. Okay. So this is for the basic idea of molecule. Some example I will give some example. I will skip the slides. A chiral molecule and chiral molecule. Some examples skip here. Right. Another one point. So non-mobile conformation. So basically, which one is the article activity? So definitely the one chiral carbon having chiral carbon 4 different group, that molecule gives to article isomerism. But this molecule is biphenyl. Here there is no any chiral carbon, but these molecules gives to article activity. The planar compound is biphenyl derived 2 sterically crowded. This molecule is plane, is oppositely plane, right? This molecule is opposite, impossible to crowd here. So flatted molecule, this molecule goes to flatted, right? So crowd, bromine, so crowd. This phenyl is free rotation here. It's, also iodine is so crowd. This molecule is opposite. So this type of molecule gives to, once again, this is the planar composition, biphenyl derivative 2 sterically crowd, and the carbon-carbon bond is thus it is a conformationally locked. This staggered conformation or chiral, they are the non-superimposable mirror image. So this molecule gives the optical activity. So same, it is allele can be chiral. This molecule having the optical activity, right? The penta 2,3 diene chiral molecules. This is for in case of there is no any chiral molecule, the molecule gives to optical isomerism, right? Another one point. So geometrical isomer and optical isomerism already we have discussed here, right? Geometrical isomerism, cis-trans isomerism, EZ isomerism, optical isomerism, chiral molecule, achiral molecule, the enantiomerism, diastereomerism, and the RS configuration we are discussing here. Another one important point, configurational isomerism to conformational isomerism. So what is here? You see the constitutional isomerism, stereoisomerism, conformational isomerism, and configurational isomerism. Here talking about naming is RS from this compound is more than one chiral center, right? More than one chiral center. Already I discussed geometrical isomerism, optical isomerism. So now going to discuss about configurational isomerism, that is geometrical and optical isomerism. Now it is another one branch of conformational isomerism. Conformational isomerism. Yes. Here the conformational isomerism. What is conformational isomerism? In case of carbon-carbon free rotation, carbon-carbon having free rotation, that is called as a conformational isomerism. I mean, this slide is once again. Yes, isomerism, it's a carbon compound having the isomerism, constant isomerism is already I told you, the stereoisomerism, conformational isomerism, configurational isomerism. Already I discussed the configurational isomerism, diastereomerism, enantiomerism, cis-trans isomerism, diastereomerism contains optical isomerism. Here another important branch is the conformational isomerism. What is conformational isomerism? Carbon-carbon free rotation, that is called as a conformational isomerism. So this is here we are talking about the conformational isomerism is interconverted by the single bond rotation. It is a free rotation, single bond rotation, it is a free rotation. This is for the right angle, it is called as a torsional angle or mostly frequently used to specific type of conformation. Here this is for Sagas projection, this is for Newman projection. This is Sagas projection, Newman projection. If the compound having the carbon-carbon free rotation, two molecules viewed, it is along with the axis of rotatable. It is interconversion of the conformation proceed by the infinitive number of the interaction conformation of low. However, the only few then of energy minima. So this is one type of the stereochemistry of rotation of carbon-carbon free rotation. In the Sagas projection, PPT not. Oh, okay. இப்போ தெரியுதுங்களா? No, wait. One second. Okay. இப்போ ஓகேவா? Okay. So just the conformation is spatial arrangement of molecule gives to constitutions and the configuration. In case of 4 atoms or molecules linked in chain manner, it's a rotation of atoms are A and T. About the inner B and C, here you see carbon and B. It is free rotation. This angle of mu leads to different mutual relation of atom A and D. As resulting of the population of set the different rotation of isomerism of conformation. So conformational isomerism is one type of stereoisomerism. Because of carbon-carbon single rotation or single parameters differentiation, such as the conformation is a single between two planes containing the ABC or BCD, right? So this is for example here the methyl group, ethane molecule. Ethane molecule means it is a Newman projection. This is for front carbon, this is for back carbon. In case of rotation is 60 degrees rotation, you rotate the this is the eclipsed formation. This is eclipsed formation. This is staggered formation. The staggered formation is stability is high and energy is low. But it is eclipsed form is energy is high, staggered is energy is high, stability is low, right? So this is torsional angle. In case of this is for another one is butane molecule. It's something different to the potential energy diagram. Here there is a difference for the anti-position, gas position and something that is simple staggered and eclipsed and gas and anti-position is there. There are the many kind of 1, 2, 3, 4 and 6 rotation is there, right? Here I am concluding my talk. It is a stereoisomerism. It is about the same formula and the connectivity, but different the position of the atoms in space. They possess the one or more stereo centers, right? Stereo centers, we are talking about the chiral, enantiomer, racemic mixture, optical activity, right? What is isomerism? Isomerism, there are two types. One is a structural isomerism, another one is stereoisomerism. So I focused only stereoisomerism. The stereoisomerism, there are two types. One is the configurational isomerism, conformational isomerism. The configurational isomerism, again two types, geometrical isomerism, optical isomerism. Geometrical isomerism concluded by the cis-trans isomerism, EZ configuration, is based on the CIP rule. And then optical isomerism, they have the chiral and achiral, enantiomer and diastereomer and RS configuration, Fischer projection, they are based on the CIP rule. And this conformation is carbon-carbon free rotation. It is angled between the cyclohexane, some other it is a carbon-carbon free rotation having, that is called as the applicable, the stereo, the chemical. So conclude by my talk. It is stereoisomerism. There are the two types. One is conformation, configurational, and is configurational isomerism, geometrical isomers, optical isomerism. So this is the basic idea of the stereochemistry of our basically the BSc chemistry student or MSc chemistry student. You must know that these type of concept and rules and regulation for the stereochemistry, right? Okay. Once again, I thank you. That gave me a wonderful opportunity to KSR College of Women to give the national level webinar of basic concept of stereo.